Okay, I will start. Good morning, guys. In this session, we will learn about how to connect the half and full wave rectifiers by using electronic workbench software. Okay, I have sent the file in your WhatsApp groups so you can see. Sure. Okay, this one your procedure cards. Okay. Mm, in this procedure, the main aim determination of ripple factor of the half and full wave rectifiers. Okay. You can see full and half wave rectifier circuits diagrams and theory parts in your procedure cards. Okay, you can see. I think you can see here, and I have attached your question paper with this, so you can see here. So you can fill the gaps and you want to send me. Okay, this one. Okay, you can read the procedure guards, and you must submit your answers before next Friday. And I have sent it in your group as a WhatsApp group, so you can download. Now we can see some main theories. Okay, some theories. This one, half effective circuits, and no. Okay, this one full wave rectifier circuits, and this one half wave rectifier circuits. Okay, the process of converting AC to DC voltage is known as the rectification. Okay, I think these things we already studied in A level. Okay, and the circuit which is used for the rectification is known as the rectifier. Okay, these rectifiers can be classified into two categories. One is known as half wave rectifiers, and second one is known as full wave rectifiers. Okay, whenever the sinusoidal signals applied as the input to this half wave rectifiers, that the rectifier only allows the one half of the sine wave and rejects the other half of the sine wave. This one's your half wave rectifier circuit diagrams. Okay, this one AC source, your AC source. This one. Okay, this one transformer and that one diode. Okay, normally we used silicon based diode. Okay, and this one resistor. It means load. Okay, if you consider your home, the current power will supply from the source. The transformer will convert the voltage value, and then if you laptop, mobile phone, maximum power supply voltage 12 or 5 voltage, it will convert. Okay, so the transformer, why we use transformer here? To convert AC to DC. Okay, and this one capacitors. Why we use capacitors here? Capacitors is used as a filter to convert the pulsating DC to pure DC. Okay, and this one we grounded here, and this one CRO. Okay, this thing we will learn here. Okay, this is CRO to measure the voltage value and to find the waveforms. Okay, and this one equation, the ripple factor. Ripple factor. Okay, the equation of ripple factor. The main aim of this practical is to find the ripple factor. Okay, the equation of the theoretical ripple factor, this one, and this one practical one. Okay, this one input waveform. Okay, for the first half cycle, when we this one AC source, the power will provide by the AC source. This one plus, this one minus. For the first half cycle, the current will follow this direction. Okay, this direction. So this diode gets forward bias. Okay, this one plus and this one plus, this one minus. Okay, the diode will get forward bias, so current will follow this direction. For the positive one. Okay, the output waveform also. For the second half cycle, the polarity will change. So this one minus, this one plus. Okay, so this side minus, this side plus for the diode. Okay, so minus 2 plus, the diode will get reverse wise. So current will not flow this direction. Okay, so in here you can see has no waveforms. Okay. For the third half cycle, here plus and minus, and the current will flow this direction. That will get forward bias. So this half cycle positive one. Okay, like that. If you use capacitor, this capacitor will filter one. Okay, filter the circuit. It's the filter to convert the pulsate in DC to pure DC. Okay, so the graph waveforms will be like that. Okay, in here in the practical we have to find the we need to find the input waveforms and input voltage and time difference. Okay, the big to big time difference. Okay, so we can see the practical and this, and we want to find the delta V. This one output, this one input. Okay, the peak value we called as input. Okay, peak value, not peak to peak value, peak value. And this one output, delta V output. So you can find the delta V and Vn, and here you can see delta V output, this difference. Okay, this difference delta V, and by 2 root 2 V not we called as input, that one peak value. Peak value means this ground to this peak value, difference between ground to peak value. Okay, and delta V output value. Okay, for the theoretical one, f means frequency, the 1 upon t time value. That's why we measure here the time value. It's a difference between peak to peak. Okay, peak to peak, this difference. Okay, to find the f, r1 already the fixed one we gave, and capacitor one. In here we have to change the capacitor's value and we want to find delta V. Okay, this one your practical, and let's we see how to use the electronic workbench. Okay, before that, this one full wave rectifier. Okay, full wave rectifier also this, and it has two circuits. This one another one. Okay, you already studied in A level. The current will flow this direction. Okay, this direction to this direction. Okay, when current will flow this one positive one, this one negative one. Okay, we will use this diode for first half cycle. Okay, first half cycle, so positive one. For the second half cycle, polarity will change. Okay, this one minus one, this one plus one, so polarity will change, current will flow this direction. Okay, we use these two diodes for the second half cycle. They also this one forward bias. For the first half cycle, this diode and this diode will be used as for no, this diodes gets forward bias, and for the second half cycle this diodes will get forward bias. Okay, that's why these things are positive, the output waveform positive altogether. Okay, the equations for the ripple factor, practical ripple factor delta V, that already we saw. This delta V not input one, and delta V not output. Okay, and for the theoretical one, if we want to calculate, we want to measure the time difference value, the difference between two peaks. Okay, so 1 upon t is equal to f frequency, and r1 fixed one we already gave, and c1 capacitors one. We in here we change capacitors value and we want to measure the delta V value. Okay, this one full wave rectifiers. And procedure you can see, first we have to connect the circuits. Okay, connect the circuits by using electronic workbench, and we have to change the capacitors value and we want to find the delta V value. Then we have to plot the reciprocal of the capacitance versus ripple vector. Okay, ripple vector graph, that y-axis should be ripple vector and x-axis should be reciprocal of the capacitance. Okay, and this one you have procedure means structure of the question paper. Okay, you should put the time value for the full wave half wave rectifier, and the frequency 1 upon t, resistance 1 already fixed one, and this one table. Okay, table you can, I think you can change the capacitor value. I think I put here 0, 20, 40, 60, 80, 100 like that. So you can find the answer for 200, 400, 600 and 800 and 1000. Okay, this one peak to peak voltage value, the difference between two peaks. Okay, two V naught. Okay, this one peak to peak voltage, this one input, the half of the peak to peak voltage, that is peak value. Okay, this one delta with the with capacitor. Okay, so you can see in your procedure cards, and ripple vector value you should calculate. Okay, the equation already gave. Okay, you should all this one ripple vector. Okay, ripple vector we already gave. Okay, two ripple vector for practical and theoretical. Okay, you can calculate the values for the half wave vectors, and um, you need to, and then you need to find the no, you need to plot the graph, that one ripple vector versus reciprocal of capacitance. You need to draw the graph in one graph sheet for the half wave vectors. You should compare both graphs, okay, for the practical and theoretical value. Okay, so x-axis should be 1 upon c, reciprocal of the capacitance, and y-axis both gamma p and gamma d, that is practical ripple vector value and theoretical ripple vector value. So you should plot the graph in one graph sheet. Okay, for the half wave rectifiers, like as full wave rectifiers, also same procedure. Okay, same structure. You can change the values in here: 200, 400, 600, and 800 and 1000. Okay, and same procedure here. And after calculate the values, you should plot the graph ripple vector versus reciprocal of the capacitance. And for the full wave also, you should plot the graph in one graph sheet. Okay, one graph sheet, 1 upon c, that is a reciprocal of the capacitance versus gamma p and gamma t. You should adjust the value for gamma p and gamma t in your graph sheets, and you can scan and send it. Okay, this one your structure, and you need to find the midpoint and upper point and lower point. Okay, uh, that's it. That thing your problem. Okay, midpoint, upper point, and lower point you should find, and you should plot the graphs. Okay. So shall we start the practical session now? How to connect the circuit by using electronic workbench. Okay, this one electronic workbench. Okay, electronic workbench. First we will see the half wave rectifiers. Okay, in here. Okay, for the half wave rectifiers, we want AC source. Okay, we want AC source, transformer, and diodes, and resistance and capacitors. Okay, and CR also. Okay, okay, so we will use AC source. So you can see the taskbar here. This one sources, this one basics, and this one diodes, and this one transistors, analog IC, mixed ICs, and digital ICs, and logic gates, and digital, and indicators, and controls, and miscellaneous, and these instruments. Okay, now we want source. There's a two source, AC source and DC source. Okay, now we want AC source. Okay, so we can take this. So okay, we can take this one, AC source, and we want transformer. Okay, so we can change, you can change in taskbar. Okay, here transformer. Okay, so we can take this one. Okay, and then we want, so we can then we can connect AC source to transformer. Okay, okay, you can connect, and then we want diode, so we can take diode. Okay, we can take diode. Okay, we can take diode and we can connect transformer to diode. Okay, double click and connect these two terminals. Okay, double click and connect these two terminals, and then we want resistance. Okay, we want resistance, so we can take and we want rotate that one, so uh, double right click and rotate. Okay, right click that symbol and rotate, and then we can connect diode to resistance. Okay, and we want capacitor. Okay, we want capacitor, so we can take the capacitor from the taskbar, and we want uh, rotated one, so double right click and rotate. Okay, so then we can connect resistance to capacitors. The capacitors will be connected parallel to the resistor. Okay, parallel to the resistor. We can connect that negative sides terminals. Okay, capacitors. Okay, and we can connect transformer to, and we want to ground the circuits. Okay, so we will take grounded one, and then we can connect. And we can connect resistor to transformer. Okay. Okay. This your I think this one your circuits. Okay, and to find the output and input waveform, we want CRO, that oscilloscope. So we can find from the instruments. So we can take CRO, that one. Okay, CRO. So we can and we can put the value for the AC, everything. So AC source. Here we use 12 voltage for the AC, because of in here, right, to put the value we can right click the AC source, and there's a component properties, and we can change the value here to 1 voltage, and we can change the frequency 30 something, so you wish. Okay, okay, changed, and here we want to use ideal transformer. Normally in the practical laboratories we don't use non-ideal one, but this one ideal one. Okay, because of the electronic we use software, so we can use ideal one. In here, if we give 12 voltage for the power supply, it will convert as 12 voltage. It does not change any value. If we use non-ideal one, if we give 240 power voltage, it will convert as 12 voltage or something. Okay, this one ideal one. And for the diode, we can right click and component properties, and in here we used 1N4001 diode. Okay, for the laboratory users we use this model of diode. Okay, so okay, and then here we put 2 kilo ohm for the resistance. So right click and component properties, and we can change the value as 2 volt, 2 kilo ohm. You can see the unit, and in here we used, in the practical we want to change the capacitors value and find the delta the output voltage. Okay, so now I change as 100 microfarad. Okay, okay, for the input. So we can find the input waveform. So connect the CRO to this source. Okay, because of input first we want to take input waveform. So connect the CRO. Okay, so we here in the CRO there's a two channels, channel 1 and channel 2. Okay, there's a two channels, channel 1 and channel 2. Okay, the channel 1 and channel 2. So we use only one channel for the rectifier, so I used one channel for input. Okay, this thing I already explained to you, so you know. Take the diode 1 and connect to the transformer and take the resistor and we want to rotate and connect with diode. Okay. And then we want capacitors. We can take and rotate and connect with resistance parallel to the resistor. Okay. We can connect capacitors to resistance and transformer to resistance, and we need ground. So we need to ground it. You can adjust. Okay, and you can adjust the wires. Okay, it's not a problem. Okay. We want CRO. So to find the input, we used only one channel, so we connected with AC source. Okay, then we change the value. Okay, and we can change the value for the resistor 2 kilo ohm and diode 1 and 4001, and to find the input we used 100 microfarad capacitor value, and this transformer ideal one only for the electronic workments. Okay, not for enjoy experimental acts. So we will give 12 voltage and 30 hertz frequency, and we can find the input waveform for the half wave rectifier. So we can run. So we want to run. So you can see the corner side the 0 and 1. So to run this CRO, you can use. Okay, we can double click the CRO. Okay. 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 You can double click the CRO. You can change. In here we used channel 1. Okay, in here we use channel A, channel 1. Okay, you can change the time deviation, time value and voltage value. x-axis should be time value and y-axis should be voltage value. So in here you can see the value we put when you are run the waveforms we can force it. Okay, so we can find the value. Here we use 10 voltage per division. You can see 10 voltage per division. So one division 10, one box 10 voltage. Okay, one box 10 voltage. So here I think you can see if you want to change the if you want to change you can adjust the x position and y position. Okay, so I adjust this one x position and this one y position. So to measure the value we can change the y position. Okay, so here I think here three boxes full boxes. So one boxes belongs to 10 voltage, so three boxes 30 voltage. Okay, and you can see I think one boxes belongs to 10 voltage, so the peak at I think third or fourth. Okay, division. So one boxes belongs to 10 voltage, so we can divide as one part 1 voltage. So there's I think three parts. So three parts or four parts. So 3 voltage. So totally we consider as four parts. So 4 voltage. Um, so 34 voltage. So one box has 10 voltage. So three boxes 30 voltage. That parts 4 voltage. So 34 voltage. So input voltage 34. And we had to find time value. So difference between peak to peak value. To find the peak to peak value, we can change the x position and the difference between two peaks. Difference between two peaks. So difference between two peaks. Okay, you can see one divisions belongs to 5 millisecond. Okay, that one box belongs to 5 milliseconds. So there is the 6 7. Okay, 6 boxes and 5 parts. Okay, so one box belongs to 5 milliseconds. So 6 box belongs to 30 millisecond, and there's I think 6 parts. Okay, so one box belongs to 5 milliseconds. So if we consider the box divided by 10 parts, so one parts belongs to 0.5 milliseconds. So there's a 6 parts, or 0.6 into 5 3 millisecond. Okay, so 6 boxes 30 millisecond, and that 6 parts 3 milliseconds, so 33 millisecond. Okay, the time difference between these two peaks. Okay, and this one time value for to calculate the frequency. So you can put the frequency value 1 upon t, f is equal to 1 upon c. Now we find voltage value also. Okay, so in your procedure guards, the theoretical ripple vector equation gamma is equal to 1 upon root 3 into 2 frc minus 1. So in this equation you can put the f value, that frequency value. Okay, and in this practical we need to find output voltage with changes of capacitors value. So for the input waveform we already find, and the input voltage 34 voltage and time difference 33 millisecond. Okay, this one input waveform we already find, and we have to find the output waveforms with capacitors. Okay, Okay, so the output voltage, output waveforms should be on now, and so we have to connect across the resistance. Okay, this one channel 1. In the rectifier circuits we use only one channel for the rectifier circuits, and there's one channel and plus and minus. We don't need to connect the minus because of already grounded one, so we can connect only positive. Okay, so now we can take the output waveforms. You can run now. See the corner side, and there's a one. So if you want to stop this waveform, you can force. Okay, this one output waveform. So you can change and take the readings. Okay, this one output waveform with capacitors. Okay, so to find the output voltage, you can change the voltage value and time values. Okay, this one for 100 microfarad. Okay, and you can change the positions and you can find the output voltage value. In here in here the output voltage at one boxes belongs to 5 one boxes belongs to 5 voltage. So in here I think if we consider, if we take 10 parts of one boxes, this one 1, so to 2.5 voltage. Okay, half of the box. So one box belongs to 5 voltage, so half of the box 2.5 voltage for the 100 microfarad. Okay, okay, this one for output. So now we can change the capacitor's value and we can find the output voltage. We already find the input waveforms and input voltage and time difference value. We already find input voltage, input time difference value, and now for the output waveform, we can see capacitors value. We can change capacitors value, and we want to find output voltage value. So I change as 20 voltage, 20 microfarad. So, okay, so you can get the output waveforms and you can find output voltage for 20 microfarad. Okay, here one voltage, one boxes belongs to 5 voltage. Okay. And here I think one boxes and 1.5 boxes, so 7.5 voltage for the 20 microfarad. Like that we can change the capacitors values and we can find the output waveforms. Okay, and now I change the capacitors value as 40 voltage, 40 microfarad, and this one output waveform with capacitors for 40 microfarad. The one box belongs to 5 voltage, so here one box, so output voltage is 5 voltage. Okay, I change the value as 60 microfarad. or 60 microfarad. So if you want to stop the waveforms, you can use pause button, and we can change the voltage time value. Or okay, in here one box belongs to 5 voltage, so I think if we divide as 10 parts, this one 8 parts, so 4 voltage for the 60 microfarad. Okay, change the value as 80 microfarad. Run it. If you want to stop the waveform, you can just pause button, and there's a waveform, and one box belongs to 5 voltage, so I think here half of the box, so 2.5 voltage. Okay, as you can. And for the cafe, this one for the cafe rectifiers. Okay, you can change the capacitors value and you can find the output values. And this one your circuit diagrams, and this one in here for the cafe rectifier. Okay, for the cafe rectifier, in here we found the capacitors value for the 0, 20, 40, 60 and 80, 100. So you can measure the peak to peak voltage value, that's input waveform. When we are at input waveform, we want to find the peak to peak voltage value 2 V0. We found as 34 like that. Okay, so input value 17. Okay, for the output waveforms, we can find output value. I think we now we we have done. So you can put the value for output voltage for 20, 40, 60, 80. So for the practical ripple factor value, you can use the equation and substitute there, and you can find the practical and ripple factor values. Okay, you can use this equation to find the practical value and theoretical value, and you can calculate the ripple factor and theoretical, practical and ripple factor value. Okay, okay, and you don't need to find the error percentage. Okay, you don't need to find the error percentage. So you can fill this gap, and you want to you can plot the graph 1 upon c, no, ripple factor versus 1 upon c, that's a reciprocal of the capacitance. Okay, ripple factor versus 1 upon c graph you should plot, and you need to plot the graph in one graph sheet for half wave rectifiers. Okay, 1 upon c versus gamma p graph, one graph, and another graph 1 upon c versus gamma t. These two graphs you should draw in one graph sheets. Okay, to find the to plot the graphs, you need to find midpoint and upper point and lower point. Okay, and this one half wave rectifiers and full wave rectifiers we can see. Okay, take the procedure cards for full wave rectifiers. See the diagrams now. Okay, this one for the full wave rectifier. Okay, this one full wave rectifiers diagram, and here we used AC source and this one diodes and capacitors and resistance. Okay, in here we can't use transformer because of in the electronic workbench software, the transformers one ideal one, so it does not change any voltage value. If we give 5 voltage to the power supply value, it does not change the value. Okay, so transformer we don't need to use the transformer for this electronic workbench software. Okay, so not need. So that's why we use these diodes. Okay, I think these things you already studied in A level. So for the full wave rectifiers, the current will flow from plus to this diodes. If we consider D1, D2, D3, D1 and D3 should be forward wires. Okay, and this one for the half wave, for first wave. Okay, second half cycle, the polarity will change, and the -2 plus the D2 and D3 should be reverse wires. Okay, this one output waveform. Okay, this one output, input and output waveforms. In here we used two diodes for one half cycle, so all output waveforms are positive ones. Okay, the last graph with capacitors, the filter one. So we want to find this delta V output waveform. Okay, V is the input one, peak value. Okay, so I think you can see now this one your circuit diagrams, and we want to measure the we want to find the input waveforms. So we can double click on the CRO and we can run the circuit. Okay, here you can change the values to find the waveforms. Normally we want AC source and diodes and capacitors and resistance and ground and resistors, and we want to rotate the resistance, and we want to ground symbol and CRO. Okay. CRO. So now we can connect these things, AC source to diodes and diodes to capacitor, and capacitors to resistance. Okay. And capacitor should be parallel to the resistance. Okay. And diode to capacitor and diode to AC source. Okay, and we want to find output one. So oscillator to resistance one's output one. So we can change the value by voltage and 50 hertz, and capacitor value 100 microfarad and resistance 500 ohm. And now we can double click the CRO. We can double click CRO. Okay, this one screen after CRO. I think you can expand the CRO screen, and you can expand, I think, in your software you can expand. So now we need to run the circuits. Okay. 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 This one your output waveform. This one your output waveform for the full wave rectifiers. Okay. You want to measure the output waveform, the delta V, you can see in the procedure that's delta V, and you can change the XY position and you can find the value. And here, uh, one boxes belongs to 2 voltage, so you can change in your voltage one box belongs to 2 voltage. So in here, I think if we divide it as 10 parts for one boxes, this one both parts, so 0.8 voltage. Okay, so 0.8 voltage for 100 microfarad. Okay, so we can change the capacitor's value and we can find the output values. If I use 20 microfarad, the output waveform like that. So you can change the voltage value or time deviation value and you can find the output value. So one boxes belongs to 2 voltage. So here one full box and I think four parts of the another box. So one parts belongs to 0.2. Here 4 parts, so 0.8 voltage. So one box has 2 voltage and another box 0.8 voltage. So 2.8 voltage for 20 microfarad. So we can see this output waveforms and we can change the value. We can change the value as 40 microfarad. 40 microfarad. Okay, we can run the circuits. This one output waveform, and here one box just belongs to 2 voltage. So I think this one 8 parts. Okay, if we divide as 10 parts of the one boxes, it is on 8 parts. 8 parts. One parts belongs to 0.2 voltage. One box belongs to 2 voltage. So one parts belongs to 0.2 voltage. So if here 8 parts, so 1.6 voltage. So we can change the capacitor's value as 60 voltage, 60 microfarad. Sorry, 60 microfarad, and we can run. We can run. Okay. Okay, one box belongs to 2 voltage. So in here I think half of the box, no, 6 parts of the box. So one parts belongs to 0.2. So 6 parts 1.2 voltage. So we can change the capacitor value as 80 microfarad. So run force. Okay, so one parts belongs to 2 voltage. So I think here 4 parts. Okay, you can assume. Okay, you can assume. So 4 parts. So one parts belongs to 0.2. So 4 parts 0.8 volts. Okay, 100 microfarad. Run the circuits. I think small difference. So okay. So 3 parts. So 0.6 voltage. Okay. So you can use like that, and you can find input waveforms and input voltage and time difference value. Okay. Okay. This one your practical full and half wave rectifiers. For the full half wave rectifiers, change the capacitance value and find the output voltage value. And full wave rectifier is also same. Okay, change the capacitance value and find the output voltage value. Okay, and this one I already explained these things. And your peak to peak for the this one I explained for only for only half wave rectifiers. Okay, because of half rectifiers and full wave rectifiers, the success same. So you can change the capacitance value in the output waveforms, and you can find the output voltage. Okay, you can change the capacitance voltage in the output waveform, and you can find the output waveform and output waveform. And this one 2 V naught, you can find the value from the input waveforms, and you can the 2 V naught will peak to peak voltage, V naught input voltage, that is half of the half of the peak to peak voltage, and this one output voltage, and this one practical reflector value, the equation we have. So you can substitute there. Here, so the peak to peak voltage T2 V naught we can find from input waveforms, and input also half of the peak to peak voltage as a peak value, and output voltage this one we can find from output waveforms. Okay, delta V. When we change the capacitance value, the output voltage change. And practical reflector value and theoretical value you can substitute in your equation, that's delta V and V naught. Delta V means output voltage, V naught input voltage, and F means that frequency value, that's 1 upon T, 1 upon time value. So resistor value fixed one we already gave, and C capacitance value, that is you change the values, the node to 100. You can change the value as node to 1000 like that. Okay, your wish. So after that you have to plot the graph. Ripple vector versus 1 upon C graphs, and you have to submit your question answers before next Friday to the Google Classroom, and you can use graph sheets, and you can download this one. I have sent in your group, so you can download and fill the gaps and uh, plot the graph in your graph sheets and scan your graph sheets and send it to us. Okay. Okay. This one your practical session. If you have any doubts, let me know.